First, I'd like to show this copy. You can all see that, can't you? Yes. And I'd like to remind Christian to look at the camera when he's speaking. It's always it's very easy to avoid doing that. I noticed when I started off talking to Jonathan Porritt, I wasn't doing that. So we try and look at the camera. And what I want to do now is to pass over to the man himself, Professor Christian Breyer, who is a world leader, if not the world leader, in modeling 100% renewable energy economies. So are you ready, Christian?
Yes, it's a pleasure to get started. So should I start just right now?
Yes, please.
Okay, then I start and I try hard to get it all done in my 20 minutes. So now it should be possible that you can see my screen. Does it work?
Yes.
Okay, excellent. So the task was, first of all, it's a pleasure that you all follow this presentation. And the title given by David to me was for 100% renewable energy systems in Europe. So I will speak more generally on Europe, but here and there, I will give a comment on the UK, of course, but also on 100% renewables in general that will go through everything here. The outline is just very brief general aspects. Then the European energy transition is the heart of everything what I tell today. Then the one or the other special aspect, let's say, let's hope that we get it through at least roughly in time, and then a brief summary. So first of all, we have across Europe a European Green Deal. Where whether it's European member state or not, I think the targets around across Europe are very, very aligned. That's very good. So we need carbon, better climate neutrality 2050, some countries even earlier, and that's important. That's very, very important. However, of course, we have also the Paris Agreement, and we have the global warming 1.5 degrees Celsius report from IPCC, and just recently got from the working group 1, the assessment report 6, and then we will get it for the working group 2 and 3 just in the months to come. And next year, then working group 3, where it's about energy systems, but it will be a lot of disappointment for all of us, because in this IPCC bubble, highly renewables are not regarded much due to various reasons. But I will come at the very end back to that. So in the end, what we know is that even negative emissions will be required in the very end, but it's very blurry what it all means. And so the real first target is, first of all, zero greenhouse gas emissions, and how this is achieved best is the question. You will be not surprised when I talk on 100% renewable that I rate this option very, very high. First of all, what is really important is we have a really fundamental rationale for electrification all around, and this means efficiency. Let's start with electricity, the first column. If we have a thermal plant, whether it's fossil or whether it's nuclear, it doesn't matter. Around about 40% efficiency is what we can expect from primary fuels in, electricity out. It can be less. We know nuclear is less. We know old coal is less. Most modern gas turbines are a bit higher, but anyway, there are huge losses. If we talk on renewable electricity from photovoltaics, wind turbines, or hydropower, then primary energy is called electricity. So everything, the electricity generated is primary energy. And then it's already on electrons, which typically is on very high efficiency. Heat is something similar. If we have really good heating systems, we get close to 100%, maybe 80 to 90% is a not bad expectation value. But then compared to electricity-based heat pumps, where we can have a coefficient of performance of 3, 4, even higher would be possible. So that means we have also, again, roughly a factor of 3 higher efficiency. The same is true for the transport sector. So to my students, I always say our cars we used, at least in the recent past, they're heating systems on wheels. because the efficiency is for a car around about 20% over the entire value chain. So from engineering point of view, huge disappointment in best possible cases, but then we are talking more maybe on even ships or airplanes, we're around about 40%. But going back to cars, comparing that to all electric, battery electric vehicles, we will be on 70, 80%. So again, a factor of 3 in between. So to sum this up, electrification is the key means to get the entire energy system much more efficient. So now let's talk a bit more on Europe. So this is, first of all, I will mainly refer on the report you see on the right-hand side that was done in the last year for Solar Power Europe, which is the solar industry or the solar association for Europe. So don't be too much shocked that there is a bit more solar here. For the case of the UK, it might be more the other way around, more wind, but it really depends on the system constraints, whether we regard the UK more as an island or more as a, how to say, it could be a basis for high national income from exporting energy. So valuable wind electricity exported to Europe, which could generate nice income for decades, then the wind share would be higher. If it's more for domestic supply, then the solar share would be a bit higher. But this just as a side comment here. When I talk on Europe, I mean this structure of Europe. So Turkey part of Europe, Belarus you don't see here, that's then part of Eurasia, but Ukraine is Europe. The decision was simply which countries are more integrated to the European side or more to the Russian-Iranian side. The Russian Eurasian side, and due to that you find this country European structure, but that should be not that surprising. In that report, and I will take most of the fundamental storylining I would like to tell on 100% renewable system from that report, because it's one of the highest standards we ever did. And this is now the basis for all research we do there. 3 scenarios. The one is called laggard, then a moderate, then a true leadership scenario. You see what it means. 100% renewables is both for the moderate and the leadership. The laggard is more what was published so far from the European Commission. But then expanded for entire Europe. And what does it mean for Paris Agreement, greenhouse gas emission, fossil fuel, nuclear? You can see in the real leadership, this is a real leadership scenario where the fossils are phased out 2040, nuclear are phased out 2040, all renewable, zero emissions. Moderate is a kind of a societal compromise somewhere in between. When it comes to nuclear, there is a phase out, but the acknowledgement that existing plants run to the end of their technical life, but new ones would not be built. So this is the assumption there. When it comes to the energy system, sorry a bit for this crowded diagram here, but you see the tip of the iceberg of the complexity. All in all, we have 120 technologies there. For various sectors, so power, heat, transport, industry, storage in between, power grid in between, what we call power to X technologies, or electricity is converted to something else, and electricity could be heat, could be fuels. So all in all, 120, a few of them are depicted. Here, of course, also all what is the conventional energy system from fossil, from nuclear, of course, bio and waste. So everything is there. So this is just this complexity. This has been now used for let's say a few dozens of studies. 3 major reports you see on the right-hand side. There is the one on Europe I talk more, but we have also a global report and a report more focusing on electricity-based fuels and chemicals, or called here power fuels. So that is a speciality of all what we do there, that this electricity to something called power to X is really regarded in much depth. So whether it's mobility, heat, fuels, chemicals, clean water, even CO2 capturing, so it's quite a lot. So, but now talking on the results. So first of all, on what we would talk on the renewable energy share on primary energy. This is the right-hand diagram. Not surprising that the leadership scenario has the 100% renewable in 2040. That was definition of the scenario. Moderate then a bit later. It's not fully 100% renewable in 2050. The reason is the one or the other nuclear reactor is simply left. A laggard, you see, deserves its name. When it comes to the fuels on the left-hand side, you see the abbreviation. So the present starting value is is 2020, or it's rather 2019, so before pandemic. But then it's the laggard, the moderate, and the leadership here in the abbreviation with these time steps. And you see that the green part, renewable energy, just goes up step by step, depending on the scenario. Not so surprising here. So now let's start with electricity generation. As said, this is an all Europe perspective. So in some parts of Europe it will be different, but I have a slide on that where we can see more the regional variation across Europe. However, with this latest, I would say, methodological assumption, but in particular, or basis, but also with the cost assumptions and technical constraints, we have been the first really showing that solar is most likely the leading source of energy for entire Europe. In all the last 20 years, we discussed the lion's share would be wind, but the true reason is that the cost of solar energy simply crashed down fast year by year. The same is true for batteries, which are most important for solar. And the consequence is that the solar shares really go up, but there, as you can see, is still a strong wind share. But in the end, energy basis is based on solar and wind. What you can see to the comparison to 2020 and 2050, the overall electricity demand strongly increases. The reason is that all final energy demand for heat, for fuels, so for the entire energy system is in the end practically all based on renewable electricity. You see a small green stripe on top. This is a bit bioenergy left, but the rest is solar and wind, a bit hydropower here on top. Yeah, that's mainly here. For heat generation, I don't go into much details here. You see in the end, it's a lot of renewable and energy-based heat, and a lot of that is renewable electricity for heat pumps or for higher temperature heat is also possible with direct electric heating, synthetic fuels, and other renewables are also there. Could be geothermal energy, solar thermal, for instance. Of course, also some bioenergy. When it comes to storage, of course, we need some storage, but I will tell you several stories about storage around. You will see them also in following slides. However, all in all, we need a lot of storage. When it comes to the output, so the discharge from storage, it's fully dominated by batteries. And the reason is they manage the day-night dispatch, in particular in a system with a lot of solar. So that means during daytime charging, discharging during nighttime. But the same would be at least partly true with wind, more wind. Wind is a rather unstable source. So solar is a bit more convenient for the system because it's available in daytime and not available in nighttime. And that's day by day with seasonal variation, of course. Wind can happen a week without wind or 2 weeks with full wind. So this is a bit more challenging from this variability, but both would work. That we know. It's then just a question of the system configuration. Anyway, batteries are very important to balance that out. And as you can see from the discharge, this is mainly batteries. We see a bit pumped hydro energy storage. This is, by the way, what we have today in Europe. It could be a bit thermal energy storage, or of course for heat is required. In a renewable system, we need a bit more gas storage. There was just not displayed here. Of course, we have today also gas storage because we have some seasonalities in gas supply. That is also required in future, but it might be then synthetic methane. It could be hydrogen. So both means here gas. When it comes to the overall coverage of the energy demand from storage, then you see we talk on a quarter roughly. From mainly heat and electricity. For fuels, we have not counted it for storage, so there will be not much difference as of today. So when you have to fill in the fuel in an airplane, it would not change much in future compared to today. The only difference is it's a synthetic fuel based on electricity. Good. Now we come more to the details when it's across Europe. So you see, all in all, and let's take this moderate scenario. So there is more than 50% is solar for entire Europe, but still a substantial, very high substantial share of wind for entire Europe. But if we look into more details, then you see it really different. So from the Atlantic coast and the Nordic, this is wind dominated. So here you see a lot of wind, so in entire Scandinavia and the Nordic, UK, but we have to be very careful. UK here means there is a lot of, in this fully interconnected system, wind electricity export to Europe. And by the way, in the summertime, there would be some substantial import of photovoltaic electricity from South and Central Europe to the UK. So this is the situation in a strongly interconnected, collaborating Europe. If we have a kind of a selfish, how to say, self-reliant Europe, all national states do it on their own, then we would have in some countries more wind and in others more solar. So in the UK, it will be more solar. And there's a diagram later on that. But all in all, it's not surprising. The more we are south, the more there is solar. The more we are at the Atlantic coastline, the more there is wind. And Spain and Portugal, they are, what you say, on the bright side of life for the decades to come, or the centuries to come, because simply they have wind and solar. It could not be better. Yeah, in the leadership scenario, it's just a variation of that. So that's not that different. Now, what is more important is here, because this tells us a lot of the hourly dispatch of such a system. Maybe I should have mentioned it earlier. When we always do such research, it's always in full hourly resolution. So every hour is respected based on historic weather data for the same time for all the resources, because it's important that for a specific weather year, we select that solar and wind is from that year, because what we typically know, if we have really good wind conditions, we have poor solar conditions and vice versa. And you even partly see that in hydropower, for example. If there is a lot of wind, there is often a lot of rainfall, then you even see more hydropower. But anyway, so this is in a then more than 50% solar dominated system, you would see this huge daytime solar capacity available. But what we've selected by intention here is the best week of the year, which is typically a spring week, so most renewable resources, and the worst, which is typically November, December, a lot of foggy clouds, so no good sunshine anymore, but due to foggy weather conditions, also no good wind. And then the overall generation is low. You see the y-axis scaling is identical, but all this generation is much lower in this worst week of a year. And then there's the question how the system reacts. And I would like to point you, first of all, you see the day-night dispatch with batteries. So there is a lot of solar. The battery get charged. This is this color here. This turquoise color, this is battery charging during daytime, and then it's discharged in nighttime, and the next cycle on the next day. But what is the most relevant in a sector coupled system, the reaction of the system is this gray part. So what means gray part? This is power to fuels. Power to fuel means this is then converted to hydrogen, green hydrogen, of course. It could be synthetic methane, jet fuel for airplanes, marine fuels. So all is based on electricity, but converted in a chemical form, what is required there if direct electricity does not work. And then you can see when low-cost electricity is available, it starts with electrolyzers. They convert electricity with water to hydrogen. They run on full capacity. If we have a worst week, then this is very low. So we have a huge flexibility. The reason is then this hydrogen can be stored in buffer storage for rather low cost. So the electricity input and the final synthetic fuel output can be simply decoupled. And this is very important. You see also in the wintertime, there is a bit more of these colors. And this is, for example, power to heat. So there is more heat demand in wintertime. By the way, there's also a bit more electricity demand in wintertime. But what is most important, this is done in full hourly resolution so that we can capture all of these effects. Since I mentioned now green hydrogen, what is the value for that? Here you see a really nice diagram for what all this is used, because currently there's a huge hydrogen hype. My response is always we have to be very careful with this hydrogen hype, but in reality we need a lot of hydrogen. But there should be always the clear guidance, direct electrification first. But there are a lot of applications where we cannot go for direct electricity solutions and then green hydrogen, typically hydrogen then to X is the route, is then the next step. But how does it work here? We have renewable electricity. With electrolyzers, we get the hydrogen. The hydrogen we can use directly, but there are not so many applications in the end. If you do a detailed analysis, then it can be converted with carbon. Of course, sustainable carbon can be captured from air. Then we have synthetic methane that can be used directly, can be liquefied. Then we have LNG, for example, could be used as a fuel for ships, could be traded. We can go for the so-called Fischer-Tropsch process. By the way, I just learned a few months ago, it was already fully established in the 1930s, also in the UK. Then it was commercialized in Germany at that time. But it's practical and old technology. We know that since 100 years how it works. The output is diesel, gasoline, jet fuel, naphtha, very valuable for chemical industry. We can go for methanol. Methanol will be the new platform chemical substituting gas, coal, oil, what we have today in chemical industry. And with nitrogen from the air, we can go for ammonia, which could be another fuel, but it's very important for fertilizer. So this is why we typically call it hydrogen to X on for what hydrogen is finally needed. So what does it mean for the energy system? This is our old energy system. It's separated. I call it very often a kind of a silo-based system because we live from the energy system point of view in various silos. There is the transport sector, not coupled much to the rest, heat sector, not much coupled to the rest, and then power sector. However, the fuels, the fossil fuels are used for all, but some, so hydropower as of today or wind is used typically only in the power sector. So this is the old system design, how it would look like in a renewable system. First of all, energy sources are mainly solar and wind, some hydropower. The rest is not anymore there. Some sustainable bioenergy might be left. By the way, when I talk on sustainable bioenergy, it's only residuals, byproducts, and wastes, nothing else. Environmental heat, this is simply from heat pumps when electricity goes in and heat from the environment is taken. But then you can see a lot of the electricity is used directly in the power sector. A lot of the electricity is used directly in the transport sector. These are our electric vehicles or trains, things like that. What can be not directly electrified goes here with electrolyzers, maybe a further synthesis, and then we have indirect fuels for the transport sector. And heat has a bit of mix of everything. That I come closer to the end, but still I require one or the other slide, so maybe I can use maybe 5 minutes, a bit more. Then what it means for the levelized cost of energy. So that means the total system cost divided by the total final energy requirement across all sectors. Then we can see that the system in the 2050s is even a bit lower in cost than today's system, with maybe only a slightly increase required on the way. From the pathway cost, maybe someone is a bit loud, maybe someone could mute the microphone, then it will be a bit easier for all. Okay, so from the pathway cost, they're very close. This moderate scenario is the least cost, but the leadership and the laggards are close. So that means if we are very,
Look,
very
sorry to
leading,
break in there, but could everybody make sure they're muted, please? Because we're getting somebody background, please. Can everybody make sure they're muted, please? Because we're getting background noise.
Okay, maybe now it works. Thanks a lot, David. Yeah, so what we can see here from the cost is also that being super low ambitious, practically failing in climate policy would cost the same as we would be super ambitious and having the job done in 20 years. I think that's maybe even the most important message. It will be a few percent points lower in cost if we get it done by 2050. So from that point of view, taking all the risk of climate change, for me, the rationale here, job has to be done by 2040. When it comes to the greenhouse gas emissions, not surprising, the consequence of the scenarios, leadership is 0 in 2040, and the moderate and the leadership is 0 in 2050. If we go for a very ambitious scenario target, then not surprising, we have the least emissions, which you can see here with the leadership. The moderate is a bit higher. the laggard is much higher, and you see it's still emitting in 2050. So such a failure is simply not acceptable. Yeah, now just sketching to another research we did earlier, only for the power sector, Interconnected Europe. And here you can see there the export, and this is the installed capacities. So not the electricity, but the installed capacities. And here you can see there will be also substantial share of solar energy in the UK. It's simply also low cost. There is also a lot of sunshine in the UK, by the way. I lived a few months in Bath and had visits in the entire region around. Of course, it was summertime, but it was great sunshine, and I enjoyed the palm trees in Cornwall, by the way. So anyway, there is sunshine. That's the point, and there's in particular sunshine when wind is not good during summertime. So due to that, also solar and wind in interaction will be important. But that's a question of exchange with Europe, but of course also with Ireland. But Ireland itself has also excellent wind conditions and some space for solar, so not too much exchange will be required. Maybe let's spend a few minutes for some special aspects, and I will be close to the end. So this is just a wrap up what I said before. What is the special role of sector coupling and flexibility? Because this is really key in a 100% renewable system. So this power to X is really the central element. And the reason is electricity can be simply used for everything. And as mentioned before, electricity-based hydrogen emerges to the second most relevant energy carrier, then for fuels and chemicals, where direct electrification is simply not possible. Flexibility is a key element. First of all, it has supply response features, so it can be done with hydro dams, with bioenergy, so there's a kind of or indirect balancing between solar and wind. Grid interconnection, very important, so in particular for balancing wind energy, so there might be more wind in the western part, less in the eastern, or the other way around, and then that can be nicely balanced. Smart demand response is very important, so just think on electric vehicles. So I ordered just recently a new car, a battery electric vehicle, and for my expectation, I have to charge it when I use it just in my town where I live, maybe once a week, every 10 days. And then, of course, I will charge it when there is sunshine on my roof, because then the PV electricity can go directly into the car. That's how it works. But there is also then vehicle to grid. We can even get it back from the car to the grid. But heat pumps are most important. Of course, they should run when there is low cost electricity available. And then electrolyzers, they simply run when electricity is very low cost. Storage, of course, is a flexibility. It can store for hours, for days, for weeks, for seasons. Electricity, heat, fuels can be stored. So there's a huge variability. Cross-border integration might be even less important than cross-sectoral. Cost reduction, at least research finds that. So the sector coupling is super, super important. And if you have efficient sector coupling, it can reduce curtailment so that we don't just spill the generation potential. And very low cost batteries and low cost electrolyzers are really key for the transition. From others, maybe we don't get too much flexibility. Maybe I skip this, I mentioned it in other words. Since we're talking on 100% renewables, I would like to give you at least an impression on what scientific field we are talking. So on the top left diagram, you can see when the known articles have been published, and you see it's mainly a discussion of the last 10 years. But the very first article was published in the mid-70s from a Danish colleague, but not so much happened until the beginning of the century. And even for the first decade of this century, not so much happened, but all the fundamental, basing started in the first 10 years, but really a rollout of the discipline and the insights happened during the last 10 years. For Europe, we know most. So this is, the hotspot in the world of research. And for where research is done, in the other regions, there is partly a really huge lack. So Middle East, Eurasia, Africa, not so much is done. From the research groups, as you can see here, not surprising, most of them are located in Europe. With Danish colleagues. So here, Henrik Lund, Martin Greiner, they both work in Denmark. Of course, German colleagues from the German Aerospace Center, Mark Jacobson, he is located at Stanford in the US. Neven Djuic, he's in Croatia. He did very important early research here, and then others. So you can see really there is a variety. I just did an update because this was from a publication only until 2018. What is the current status? You see there is continued growth of research in the field. So also 2019, 2020, more and more articles came online. We will have a new record in this year. This is just recording until mid of the year. And we expect 100 articles by end of the year. So again, grows very, very strongly. Maybe I do not tell too much on PV, only the fundamental message is in major international research, in particular what is used for the IPCC, solar energy is downplayed by failures of those who did the scenarios. To cut it short, in this year there have been 3 major articles published, all with the same fundamental insight. The integrated assessment models, they're mainly used for the IPCC. They have no clue on solar energy. To cut it very short, the reason is wrong cost, wrong modeling. So they're, what we say in science, they require a renewal to make it short. So that was then all. So just for the summary again, so low ambition pathway in Europe is a burden for society from both climate and economic perspective. This moderate scenario, so that means 0 emissions by 2050, appears to the most economic pathway. However, a highly ambitious climate change mitigation pathway is possible, which would result in more investments, but with benefit of lower per unit energy cost in 2050 and slightly higher pathway cost. So all in all, we should have a revised target by 2040, and there is already discussion now on that. Power to X is the central element of a future energy system. Solar PV, at least for entire Europe, even more global, is the prime source of energy, complemented by wind energy, which is the second most relevant one. In some regions in the world, in particular UK, wind will be in the lead, no doubt on that. And hydro and bio will support. I have a bullet here. So the UK energy transition is comparable to all what happens in entire Europe, but wind will be different. And the 100% renewable energy system is fast growing research field, serving the societal needs we really need. And of course, I would like to say thanks to my entire team here, as you can see, from all various countries around the world, with a lot of different native languages. They all talk on solar economy, but solar means the physical solar. So all what we get from the sun, which is wind, hydro, bio, and solar. Okay, then many thanks. And I'm very open for all your questions. So just let me know for our Q&A.
Okay, thank you very much, Christian. We've got 2 questions posed on the chat line. One from Rick Greenuff, who says, what do you think is the future for utility scale solar thermal? First, that one.
Yeah, maybe first a precision, solar thermal for power or solar thermal for heat?
Rick?
Just unmuting, sorry. For heat, Christian.
Okay, yeah. It depends where in the world we are, I would say. So solar thermal for heat, in very sunny regions might be very attractive, so utility scale, for industrial processes. So there we can get it on high temperature. And that's really, really interesting. The challenge might be to get it integrated on site. So in our modeling, we're very positive on that, by the way. But then we got regularly feedback. Of course, you can have very high temperature, concentrated solar thermal heat, utility scale heat for cement production, for instance. But if there is a cement mill around, there is always a lot of dust, which is not good for your concentrated solar. So there might be more local barriers and restrictions. But in principle, there should be a demand, in particular for high temperature heat. When it comes for utility scale solar thermal heat for district heating, then the views are quite diverse, I would say. The only country where this is done on a more active level is Denmark, but it's not copy-pasted in other European countries. So they even do seasonal solar energy storage, so collecting it with solar thermal in the summer and using it then in the winter, storing it underground, and it works for the Danish conditions. but no other European country is going for that. I'm still not yet sure what is the true reason for that, whether it might be specific costs, specific conditions, but at least it works nicely in Denmark. For the overall condition, I would say utility scale solutions. It's in the end, it's always based on the true cost. And if you have access to extremely low cost electricity, then of course the same makes quite a lot of sense on the electricity basis. And if we talk on district heating, then of course with electricity based heat pumps for district heating, and then solar thermal may have hard times. On rooftops, I know currently, for example, there is a kind of a end user parity in several European countries with solar thermal on the rooftop versus solar electricity based heat pumping system, because there is lack of sunshine in the winter in any way, whether it's thermal or electricity based, but the heat pump you can use in the winter with wind electricity, of course. But cost-wise, the race was won with solar PV-based electricity on roofs and heat pumps. However, in several countries, there are still investments in the solar thermal route, and the reason is simply they get subsidies much higher. And then it's not based on true cost, but from end user perspective, it still makes sense if someone just hands over you the money for free, and then it makes sense for you, then you go for it. But all in all, utility scale solar thermal, at least in Europe, I would not expect much to come from. And the reason is low cost electricity from solar and wind. So it's not due to the solar thermal technology itself. The competition just gets much harder.
Okay, thank you. Another question from Jeremy Harrison. Given the heavy dependence on solar PV in your scenario, there will be a huge interseasonal balance. This will require storage on order of magnitude greater than for diurnal storage. Not true in the case of the UK, but anyway, Italy and Spain, that sort of thing, I suppose. But your storage mix is dominated by batteries, which are not so well suited CF hydrogen for interseasonal storage. Can you explain your selection of storage solutions?
Yes, many thanks for the question. First of all, this is fully true, no doubt on that. But due to that, in particular for the geographic position of Europe, it's super important to have both solar and wind, because we have much more wind in the winter half year, we have much more solar in the summer half year. And then if we have both, we have the fundamental resource complementarity of both. So this is, first of all, the most important first point. But in the end, it's a cost optimization. So people don't ask you too much whether it's the most technical sound system. They ask you for what system we have to pay the lowest amount of money where the bills are low. This is the question. And if then alternative solutions break this, how to say, seasonal symmetry of solar and wind, but for less cost, then you go for this, I would call it as a physicist, as a symmetry break, but it simply costs less. And this less means that more from the summer is all in the energy system, also on a seasonal level, shifted to other parts of the year, which will be then autumn to spring, but it's not in the power system. In the power system, this is just where we harvest our primary energy, and the electricity demand as of today, this is highly inelastic. We now want to have our online meeting, we run our computers, we need the electricity now. There is no discussion whether it can be an hour earlier or later. No chance on that. So this is inelastic. This has to be simply managed. However, there is a demand when, of course, there is also no question when the airplane should be refilled with their jet fuel, but we can bunker them as we do it, by the way, today. So we have storage for fuels for many months across Europe, also strategic reserve, but also permanent storage. We have typically high storage level of gas, seasonal gas storage underground in Europe during the summer, and consuming more gas in the winter half year for heating and other purposes. This is usual practice since decades. There is nothing new that we have this seasonal dispatch, and that we will do the same in future. But now the primary energy is not anymore a climate disturbing, destroying fossil gas we pump out of the Northern Sea region or somewhere else. It's electricity we have with solar and wind. We convert it with electrolyzers to hydrogen. We may convert it to something else or store the hydrogen. That we can also store, by the way, underground as we store methane. It can be done in rock caverns, in salt caverns, even in steel pipeline tanks. Even that would not destroy the business case. And by the way, all these storage options are used. So such a hydrogen storage is currently built in Germany. The steel tanks underground we have in refineries since many decades. So this is just standard technology that will be used. But a lot of this hydrogen is converted to marine fuels, to aviation fuels, and that we would store as we do it today, underground or on ground in larger tanks. And of course, not everything is done in the summer and everything is consumed in the winter. So the overall storage share will be simply a bit lower. But that dispatch is required. But luckily, to store just huge amounts of jet fuel, that is not that costly compared to battery storage. The diagram I've shown was explicitly the output of the storage for solar and heat, but what is converted to other sectors simply is done in today's also available storage options. So that is not a super big deal, I would say. When it comes to the storage capacity, the picture is vice versa. Then it's dominated by gas storage and only a little contribution from battery. This is the question on capacity and throughput. Why this is a huge difference? As you said, a diurnal storage is typically used, let's say, all in all 300 days a year, while a seasonal storage may be used in the full charge cycling once or twice a year. So you have a factor of 150 to 300 in between. So that means that you need a huge capacity for seasonal storage, while the output is rather low because you have only once or twice a year the full storage discharged, while the battery capacities are comparably small, but you use them daily, so the throughput is much higher. What we find in our results that from the electricity throughput, 90% is batteries. And don't expect too much from seasonal storage coming back to the energy system. This is not required because we have so much solar and wind capacities in the system that we simply have in most times a lot available when we have low solar and wind in total, but then we simply go down with electrolyzers. They can be regulated within seconds, so no problem on that. And then we simply would not produce the hydrogen. That indirectly would balance out the power sector. So not much of this chemically stored energy would ever come back to the power sector. This also means of efficiency. Hopefully I've roughly explained this complicated part with seasonal storage.
Okay, thank you. Yes. Next question from Steve Harper. What we can say that wind and PV is known technology that is easily implemented. To meet high renewable use by 2050, it makes sense to throw all of the money behind that. Other less well-developed technologies can catch up. How does Christian see the balance of where investment should go first?
Yeah, thanks for this most important question. So first of all, we need the input to the system, and there the investments have to go first, and this is solar and wind. This is very clear because otherwise we have this renewable energy deniers. They tell you, oh, we do not have enough renewable electricity, so we cannot do this. So all policies which block investments in renewable electricity, solar and wind electricity, these barriers have to be removed, and there are many barriers. Second, we need power grid interconnections. They typically take 20 years if we are successful to get them built. So that has to be started 10 years ago. So that's very important. So maximum pressure on such scenarios to really understand what in such a renewable electricity-based world is really required for power grids so that the starting of that can be initiated as early as possible. Luckily, from the cost point of view, it does not destroy the business case if you have underground cables. And typically there, the resistance is completely different. So if they can be buried, but this has to be done. We need much more energy research because all these technologies can be improved, can be lower in cost and so on. What is more needed than investments is the political willingness to set the right regulation and the right framing. So when combustion cars will be not anymore accepted on roads, this has to be clearly decided, a clear roadmap brought on the table and then executed, because then everyone can adapt to that. The car manufacturers, the infrastructure around, the people, you simply know when your last combustion car was bought. And then the next one is simply something else, but everyone can prepare to that. The same is true for industry. Industry, they go for reinvestment cycles every 20, 30 years. They have to plan. So if you're operator of a steel mill, you have to know when it's absolutely required to switch from coal to hydrogen-based steel making. And you need a regulation around, because you are captured in this 20, 30 in reinvestment cycles. So again, to the question where the money should go for is, first of all these easy to electrify parts. And in particular, where the money should not go for is everything what has to do with fossil but also nuclear and the respected infrastructure. This is practically all stranded money. And then the low-hanging fruits first, which is for sure solar, wind, maybe here and there already some storage, then grids, the cars, so battery electric vehicles, heat pumps, all these kind of things, they should be already in full rollout.
Thank you. Thank you. Keith Condacor asks, how much easier is it if we take more solar from North Africa? That should be less seasonality as we move south. Yeah. Also, yes, it's quite sunny all year round in Casablanca, I suppose. Also, anything helpful from wave and tides?
Yeah. First of all, from the intuitive point of view, I can understand this point very well. And it takes you some time to understand what are the drawbacks. So to give you some background, 10 years ago, a bit longer, 10 to 15 years ago, there was the Desertec concept broadly discussed, which had the fundamental idea of taking solar energy from North Africa to Europe. And there is a Desertec Foundation. I'm even a co-founder of the Desertec Foundation, so I know quite well the background of this entire idea. The point is, it simply does not pay off. The sun is shining everywhere, also in Europe, also in the UK, in Spain, in Italy, in Germany, also in Northern Africa. And nowadays, solar electricity is so extremely low cost that the power lines are simply too expensive to get it transmitted where the demand is. It's simply too expensive to do it with electricity. And the reason is, in Northern Africa, the sun might be 20% better than the average of Spain, maybe 40% better than in the UK, but the overall electricity generation cost in the UK utility scale is less than 5 euro cents today. So it simply does not pay off to build 3,000 kilometers of power lines, which are expensive and takes you decades. But there is a huge but. Why not using this extremely low-cost electricity and convert it to synthetic fuels and chemicals? Because they can be traded globally, as we do it since 100 years, with fuel, with oil, with others. We have even pipelines. So this is a perfect business case for Algeria. They only have to switch to green hydrogen and then pump the green hydrogen to Europe, where they pump today fossil gas. So they even have the infrastructure. It's great for them. They can continue their business, but just switching the fuel and everything is sustainable. So for them, it will be great. So there should be this strong collaboration. And by the way, if you put it once in a ship, it doesn't matter much whether you import it from Morocco or whether you import it from Chile. That costs you maybe 3% more of the total fuel. And then you can do a kind of a global portfolio strategy from where you import it. But from a European perspective, we should do everything to accelerate economic growth in Northern Africa. That would ease a lot of other problems as well. So as a European patriot, I would strongly vote for having such synthetic fuels and chemicals in Northern Africa. Resources are excellent, as we know. But it would help everyone involved a lot. When it comes to wave and tidal was done already in the 60s, but still it's too expensive. Wave energy, I'm very sure we will see much more wave energy. There are really good developments in the last years with new companies, new ideas, new technologies, where a lot of the previous problems have been fixed. And I would expect wave energy to contribute much, much more in future. It might be the more disruptive technology to offshore wind, to be honest. And in more the tropical region, not so much in Europe, but in tropical regions, we will even see offshore floating PV, because if PV in principle is very low cost, then you can put it on floating offshore and it's still low cost. And for island supply, it's very important. I think for Europe, not that much.
Right, next one from Fred Starr. How does one manage the transition in Britain? There is going to be a day in which people stop using gas. In preparation, there would have to be a huge increase in the amount of electricity cables, which won't be used for a long time. He wants your response to that.
Yeah, this is then something which we still require more research, to be honest. It's not yet really understood well what we should do on a distribution grid level, whether we should still keep some gas installations there. It would be then synthetic gas or hydrogen, or whether we should go more for electricity, but then we would need a much stronger distribution grid for electricity. Maybe the best solution would be to have still a stronger distribution grid, having heat pumps, but more thermal energy storage. Maybe with district heating, we can balance it more easily. So where we have communities already connected to district heating, we simply have to remove the gas boiler and put their heat pump there. And then it's easier to balance it with power lines, but also with thermal energy storage. This is also a really important flexibility. So we call it the power to heat when a lot of excess is available from wind or others. So that would be nice. But this is an infrastructure debate which requires early and open-minded discussion. And there might be even different communities with different solutions. We need to be prepared. In any case, what is very important to have a much higher efficiency in buildings so that we don't need too much heating, because in the end we talk on heating when it comes to that, because that would lead to a smaller dimensioning of the entire heat supply system in the end.
And finally, from Alistair Yule, what overall reduction in energy demand does 100% renewable energy require compared to today, if any? Do lifestyles need to change?
I like this question. Typically, we get hours of discussion because there are two fractions in the room. Once I'm a strict supporter of one, but I start with the other first. The other is degrowth. So every one of us requires reduction in our consumption, that in a dirty energy environment, it's enough for everyone. This is something which is typically discussed much from social science researchers. But maybe they do not yet fully understand what you can do with really renewable, low-cost, scalable electricity, because it roots back to the idea we require energy, but unfortunately it's dirty, air pollution, climate change, international conflicts on resources, all these kind of issues. So better we use less, we do not fly anymore, and so on. This is the degrowth fraction. I can tell you this is for everyone who can personally organize to use less energy. We all should be grateful, and it's perfect. You can do a hobby, you can do a sports discipline out of that. What is the minimum energy requirement you need, and still enjoy, maybe even enjoy more your life? I would not argue against that. But, and then comes the huge but, I'm fully convinced that 70–80% of the people enjoy the easy and convenient life. So they don't want to care on that. They want to pay their bills. If it costs less than today, they're even more happy. They don't want to worry about that, but they don't want to have a bad mood with using energy. So it should be still sustainable as much as possible, but please, no change of lifestyle. This is the attitude of the large majority of people. And now, as a question, as an engineer on my side, is can we design an energy system where, first of all, those using less energy are happy, but the others who don't care at all can still have a fully sustainable energy supply? That's my engineering question. And the simple answer is sure, no problem. And the reason is low cost, scalable renewables. So if we have a system based on solar and wind, our environmental impact is very, very low, at least compared to all others we know from fossil and nuclear. We can convert electricity to every form of energy. We can do everything what we want to do with low cost electricity. So there is no need for that. However, if, and due to that, I said it just before, whenever we can have more efficient buildings, it's great. Remember my second slide in the beginning, efficiency matters, of course. With electric vehicles, we need a third of the primary energy. With heat pumps, we need a third of the primary energy. With electricity, renewable electricity in the power sector, we need a third of the primary energy. So we can realize huge primary energy efficiency gains if we simply switch to renewable electricity based on solar and wind. But there is one but. If we do these power to X processes, then typically we get a factor of 2 penalty. So you need 2 units of electricity to get 1 unit of synthetic fuel or chemical out, roundabout. It can be a bit more, a bit less, but the factor of 2 is a good approximation. So that means synthetic jet fuel, 1 energy unit of synthetic jet fuel requires 2 units of electricity input first. And now is the question, what of these 2 factors is more relevant? So the efficiency gain with electric cars, with heat pumps, with not any more combustion, power generation, or this synthetic conversion. This was a research question. It took me more than 10 years to get a solid answer on that. The solid answer is if we compare the 2050 energy system with the energy use and the efficiency standards as of today, we would require twice as much primary energy as in a 2050 energy system, which is practically fully based on renewable electricity. So to answer the question, on the primary energy side, we can gain 50% while even, how to say, rolling out our lifestyle of energy poverty to every single human on the planet. So I was talking on Europe, but we do research for the entire world. And the same is true for the 1.7 billion Indians we have in 2050. They could live on the same energetic standards in India. Not surprising, it's mainly solar, but they have one of the best solar resources on the planet. So they're also on the bright side of life. You can do that. So the point is we can have even improved energetic lifestyles for everyone, but the precondition is we have to go for renewable, scalable, low-cost primary energy input, and this is in the end solar and wind.
Okay, thank you. I've got a comment from Steve Harper who says a game changer he saw last week is the Kelda, K-E-L-D-A, air-powered shower. It uses half the water and thus half the heat for domestic hot water. These are the things that reduce demand. And Pete Roach says, can we get a copy of the slides emailed round, please? Yeah.
Sure, all slides will be available. I will just send it to David. And there's even more in the backup, so you can enjoy the one or the other slide more. They should be at least roughly self-explaining, but they fully go within the storyline. And maybe one thing I would like to point out, because the topic was simply Europe, so I did not talk too much on the UK. We do detailed review of all what is published with 100% renewables. And to say it quite clearly, I do not know a single really excellently well done study for the UK. In particular with geographic resolution, so that we see what happens in different parts of the UK, how it can be interacted. It's rather clear that in London, not all energy can be provided, what is consumed there. So it has to be from regions around. And this has not yet been done on a solid level from my point of view. And hopefully I'm not insulting, but I would say it has to do that many researchers in the UK are flooded with fossil CCS and nuclear money. So they are not allowed, or practically it does not make economic sense for them to talk on 100% renewables because they would not get further funding.
Absolutely, yes.
That's
yes.
really a problem, what I noticed for the UK too.
Absolutely, yes.
Frankly,
we need this study very badly, not just so that we can produce a one-off press release, as important as these things are, but so that we can use this as a campaigning device and also unscramble all the details which you produce with your models about the demand profiles and about the storage issues and so on, so that we can explain these at different times and in different venues, organising different events. It would actually be very useful if within the agreed package, the price that we've got at the moment, you could, excuse me bowling you this one, if we could have some sort of interactive almost game thing so that people in universities and schools could download, so that they could maybe opt for different options. Now, if you could produce that, now that would be a major winner. Anyway, I just chuck that there. But anyway, we have to raise money for this. We've still got a long way to go. I mean, speaking personally, I'm prepared to put thousands of pounds in from my pocket, but it's not limitless. We have to raise a lot of money, and this gets so if all of you could push very strongly on this, you know where the GoFundMe site is. I'm not just talking about individuals putting in money, but also getting other people too. If you could really push this into, put some effort into all that. But today we have a specific fundraiser, which I want to move on to now, and that is an auction for, first auction we're going to do, a signed copy of Jonathan Porritt's great work, Hope in Hell. And so I'm asking for bids here. The reserve price is £20. So now you can bid either through unmuting yourselves and bidding, or through the chat line. So I'm looking for a bid of £20. Who's going to start this off? Who's going to start off with a bid of £20? Steve Harper has bid £30. Okay, so we have an advance on £30 and a signed copy of, what's that? 40 from Nick. Nick Carroll has bid £40. Have we got an advance on £40 for a signed copy? I mean, there's no others around of Hope in Hell. Have we? Steve Harbour, 50. Steve Harbour has gone 50. It's on 50 at the moment. What advance have we got on that? £50 so far from Steve Harper. I mean, you know, how many of these signed copies are you going to get around from this world famous leading green author? £50 so far. Have we got any advance on £50? £50, it's not very much.
Come on, Steve, it's a good bargain. Go on, 60.
£60 from...
Oh, sorry.
From Nick Carroll. £60 from Nick Carroll.
Taylor.
Have we got any advance on £60? £60, 70 from Steve Harper. There's just two people in this race so far. Have we got any later entrants? £70 from Steve Harper.
Right, right, David, Mike and I are going to top the lot and go 100.
£100, £100 from Mike and Joan, isn't it? Yes. £100 from Mike and Joan. Yes. So far, anybody else? I mean, you know, this is going to be a historic piece of publication which you can pass down to your grandchildren and great-grandchildren. This is it, where it all started, for the 100% renewable energy. £100. So far, have we got any advance on that? £100. I mean, okay, this is going once, going twice. Nobody coming in at the last to grab this. Yes, going third time. It's £100 to Mike and Joan for the signed copy of Hope in Hell. Right, but I haven't finished yet. I haven't finished yet with the auction. I've got two two books of mine I wrote many years ago. One I produced in 1995, and it was called The Low Cost Planet, in which I'd say we'd be saved at low cost. Well, anyway, yes, and people thought I must be joking. It only sold 1,000 copies at the time. But what about now? You can look through this and think, well, where was I prescient and where was I talking nonsense? I must say things have moved on a long time since then. But anyway, so we'll auction this one off. So have I got any bids for this? Reserve price of £20. I mean, this is going to be signed by me, of course, as well. £20 from this. Have I got anybody? Anybody bid £20 for Low Cost Planet? Put it in your library. No, nobody.
Oh, go on. I think Steve made a bid, but I'll bid. What was it, Steve? £20.
What have you bid, Steve?
I'll give you 20.
Yeah, I bid 30. Yeah.
30,
Oh.
30 from Steve. 30 from Steve. Have we got any higher bids than that? Nick, you would like to come in higher than that?
No, I was bidding against Steve beforehand. I think Steve ought to have a memento of this exceptional occasion.
Okay, Steve. Going once, going twice, going 3 times, you get a signed copy of The Low Cost Planet. And finally, a really seminal book. 30 years ago, I wrote something called Green Energy, a non-nuclear response to the greenhouse effect for the UK. And it's got some really fantastic things in it, which you'll really love to laugh at and so on, about how outdated, but some was quite prescient. I mean, there we are. There's a copy which actually is by a guy called David Milborough of offshore wind power there, providing all of UK electricity in today's. And this is another figure which you can see this is a list of all energy sources without environmental impacts, as you see. Yes, I thought that was a good one. I sent that into the publisher and they say, look, you've missed something off on this page. And I said, no. Anyway, go on. So what am I bid for this? Again, I'll sign copy and send it out to you. What am I bid for this?
I'll stand on £30.
£30 from Nick Carroll. Have I any more bids for this?
David, I have a copy of this, and I can say it was one of my key inspirations when I first came to the UK from Germany, so I can highly recommend it as a highly inspirational book. I won't bid because I've got a copy ready, but I would encourage high bids for this historical document, and it was very impressive.
You're rotter. You just put the bloody price up, mate.
Well, how much did you bid? Was it £30?
Oh, I believe it was 20. No, it was 30.
Okay. Have we any other bids for green energy? This inspirational text.
It was, yeah.
But okay, going once, twice, 3 times to Nick Carroll. Okay, right. Well, I think that'll do for the fundraising, but a lot of that heavy lifting still has to be done as far as this is concerned. I mean, we have to, as far as the contract that we drawn up, the company drawn up with Christian. Well, in theory, at least, we've got until the end of the year when the contract finishes, but hopefully we'll have something ready before December the 31st. So anyway, thank you to Christian in particular, of course, thanks also to Jonathan Porritt, who isn't here, and thanks to the rest of you for all of this. So on that point, we'll end the session. Okay, so
Thank you.
cheers.
That was really
Thank you.
good.
Lovely to meet you all.
Yes,
It was a
that
pleasure.
was really brilliant, Christian. That was fantastic.
Yes.
Thanks a
And,
lot.
And please send us the slides.
I will send it. Sure.
Thanks
Okay.
so much,
See ya.
David. Thank you.
Any questions?
Bye.
Cheers all.
Bye. Bye.
Bye.